Hello and welcome to The Explainer. Today we are going on a truly epic journey, deep inside the human body. We're going to follow one tiny, heroic medication molecule on its incredibly dangerous mission, right from the moment you swallow a pill.
You've probably done it 1,000 times, right? You pop a pill for a headache or for an infection, and you just kind of trust it's gonna work. But have you ever really stopped to think about it? How in the world does that tiny thing navigate the absolute maze of your body to find the one single spot where it's needed? It's a journey with way more twists and turns than you could ever imagine.
So that's what we're doing. We are going to turn our medication into a character. Think of it like a tiny secret agent, a single molecule with one critical mission: reach the target. But to pull it off, it has to survive a trip that is part obstacle course and part demolition derby.
Okay, so our molecule's mission kicks off the second that pill goes down. But just getting into the system, that's the first huge challenge. And trust me, it's not as easy as just knocking on the front door.
Before our little agent can even think about its real mission, it faces this three-part entry exam. First up, dissolution. It's got to break free from that solid pill. Then, absorption. It has to somehow get through the heavily guarded wall of your gut to slip into the bloodstream. And only if it makes it past that checkpoint does it finally get to the distribution phase, getting swept away on the superhighways of your circulatory system.
But there's a huge catch. Right after it's absorbed, all that blood from the gut goes straight to the liver. This is something called first-pass metabolism. And you can think of the liver as a security checkpoint that charges a serious toll. It chemically destroys a big chunk of our drug molecules before they even get a chance to reach the rest of the body. This is a massive reason why the dose you take in a pill is often way higher than an injection. You have to account for all the agents you're going to lose at this very first toll booth.
All right, so our molecule's in the bloodstream. You'd think it's home free, right? Nope, not even close. Now the body's real defense systems kick in a high gear. The mission just went from a stealthy infiltration to an all-out action movie.
So our cells have their own security, and they are not messing around. They have things called efflux pumps, and the best way to think of them is as cellular bouncers. As our drug molecule tries to get into a cell, these pumps can literally grab it and just throw it right back out. They're a major line of defense that tries to keep drugs out, especially from protected places like your brain.
And all this time, our molecule keeps circling back through the liver, which is basically a giant molecular demolition plant. In here, a whole crew of specialized enzymes, especially the cytochrome P450 family, or CYP enzymes, is on duty. Their entire job is to find foreign things like our drug and take them apart, piece by piece, so they're easier to get rid of.
This constant process of being broken down and removed leads to a really crucial concept: a drug's half-life. It's actually a pretty simple idea. How long does it take for your body to get rid of half of the drug you took? That number, the half-life, is the absolute key to understanding why you take your medicine on the schedule you do.
And that's exactly why dosing schedules are so different. You take something like penicillin, it has a really short half-life. It gets cleared out of your body super fast, which is why you have to take it multiple times a day to keep the levels high enough to work. But then you have an antibiotic like ceftriaxone. It has a much longer half-life. It sticks around for a while. So a single dose once a day is usually enough to get the job done.
Okay, our heroic little molecule has survived being dissolved. It paid the liver's first-pass toll, it dodged the cellular bouncers, and it evaded the demolition crew. Against all odds, the few remaining survivors are now closing in on the target. This is it, the climax of the entire journey.
So what is this target? Well, for most drugs, it's a specific protein called a receptor. The easiest way to picture this is to think of receptors as tiny molecular locks that are all over the surface or even inside our cells. Our drug molecule, it's the key, and it has traveled this whole crazy way hoping to find the one specific lock it was designed to fit. Now, a drug key can work in one of two main ways. It can be an agonist, that's like a master key. It fits the lock, it turns it, and it triggers a response inside the cell. Or it can be an antagonist. This key also fits the lock, but it's designed to just jam it. It doesn't turn it or activate anything itself, but by sitting in the lock, it physically blocks the body's own natural keys from getting in and doing their thing.
So our molecule hit its target.
Mission accomplished. Victory's ours, right? Well, sort of. Let's zoom out now and look at the bigger picture. Because no drug and no mission ever happens in a vacuum. There's always collateral damage.
This brings us to one of the biggest questions in all of medicine. If a drug is designed so carefully for one specific job, why does it almost always cause other unwanted effects? The answer goes right back to our lock and key story.
It really boils down to a couple of main reasons. First, our key might not be perfectly designed. It could be a bit of a skeleton key, able to fit into other similar-looking locks on different cells around the body, causing off-target effects. Second, the correct lock might just exist in lots of different places. A drug that blocks a receptor to treat one problem might also block that same receptor in your salivary glands, leading to that classic dry mouth side effect. And sometimes the effect we want in one part of the body is just not what we want somewhere else. And it gets even more complicated when you're taking more than one medication at a time. Now you don't just have one secret agent on a mission, you have multiple teams of agents running around. And believe me, their missions can definitely interfere with each other in some pretty dangerous ways.
Okay, check this out. This is a classic example of how these missions can totally collide. The heartburn drug, cimetidine. Its main job here is to basically throw a wrench in the gears of the liver's demolition plant. Now let's say a person is also taking the blood thinner warfarin. Well, warfarin depends on that same demolition plant to get broken down. So because cimetidine is interfering, warfarin just sticks around for way too long. Its levels can build up and up to dangerous heights, which seriously increases the risk of bleeding.
So, we've followed our molecule on this absolutely wild ride. From a simple pill to a complex mission with allies, enemies, and unintended consequences. It's just a powerful reminder of the incredible, mind-boggling complexity that's humming away inside of us all the time.
So let's just trace that incredible path one last time. The mission began with ingestion. It survived the gauntlet of getting absorbed. It fought back against the body's defenses. It hit its specific target, and then, finally, it was eliminated. It is an incredible dance between chemistry and biology, and it happens every single time you take a pill.
And that just leaves us with a final, fascinating thought. Every single step of this journey we just followed is a potential target for scientists. As we get better and better at mapping this whole process, are we getting closer to designing the perfect molecular agent? A drug so incredibly specific that it completes its mission with flawless precision. And zero collateral damage? The journey for science continues. Thanks for joining us on The Explainer.